Chemical nanosponges are nanoscale materials designed to trap, hold, and release molecules using chemistry, not magic. At the simplest level, a chemical nanosponge is a tiny solid particle made from a highly cross-linked network that contains many internal cavities and pores. Those cavities act like molecular pockets where other molecules can sit. The word nano matters because these particles are typically tens to a few hundred nanometers across. At that scale, surface area is enormous relative to size, and molecules can diffuse in and out quickly. The word sponge matters because uptake happens through pores and cavities, not by dissolving. A nanosponge usually stays insoluble, but it can soak up guest molecules from its surroundings. The most common example in chemistry is the cyclodextrin nanosponge. Cyclodextrins are ring-shaped sugar molecules with a water-loving outside and a water-avoiding inner cavity. When chemists chemically cross-link many cyclodextrins together, they lock them into a permanent three-dimensional network. That network contains the original cyclodextrin cavities plus extra voids formed between crosslinks. The result is a rigid, porous particle with many places for molecules to bind. Molecules are captured mainly through non-covalent interactions. Hydrophobic parts of a molecule can sit inside hydrophobic cavities. Other regions interact through hydrogen bonding, van der Waals forces, or electrostatic attraction if charges are present. Importantly, this is an equilibrium process. Molecules are not permanently trapped. They can leave when conditions change. Because the structure is chemically tunable, nanosponges can be designed to load molecules efficiently and release them slowly. Release usually happens by diffusion, combined with gradual weakening of these interactions. In more advanced designs, release can respond to pH, enzymes, or redox conditions. This chemistry makes nanosponges useful. In drug delivery, they can improve the solubility of poorly soluble drugs, protect them from degradation, and provide controlled release. In environmental chemistry, they can capture pollutants like dyes, pesticides, or heavy metals, and then be regenerated by washing. In materials and sensing, highly porous nanosponges offer strong interactions with gases and small molecules. A good way to picture a chemical nanosponge is as a rigid nanoscale city of cages and channels. Molecules move in, get held by weak chemical forces, and leave when the balance shifts. Structure creates function, and chemistry controls the structure.